thanks everybody for coming. I was worried for a bit. Hi, I'm Kostas. I'm co-founder of Data Artisans, the company we started when we open sourced Apache Flink. Who has heard about Apache Flink in this room? Okay, good enough. Very nice. Some of you may find this presentation to be less technical than you would hope. I'm super happy to dig deeper afterwards, so please come find me. Yeah. So the first thing that I would like to talk to you about is data streaming in general. So this is a talk about Apache Flink as a stream processor. If you are following the space, going to the recent conferences, you might have noticed that data streaming is becoming more and more popular. And there are very good reasons for that. But the first thing is, what is data streaming, right? So I hear a lot of people sort of equating data streaming with these low latency, real-time applications. So think of, either high-frequency trading or fraud prevention in banks, these kind of things. Yeah. This is a part of data streaming, but it's really it's just one part of data streaming. So actually, this is not a true statement. So for me, data streaming is actually enabling the obvious thing. So if you think about it, most data in your company is not static. Yeah, the only data that is probably static is the location of your buildings. Everything else is continuously produced. And streaming technology just enables this obvious thing, basically continuous processing on data that is continuously produced. And in most companies, you're actually already doing data streaming. You might not be realizing it. Yeah? So basically, the idea is that with new technology, you can do it much, much better and be explicit about it. So if you think about, the different places where analytics go, you have your sort of real-time data. People usually keep that in a message queue like Kafka. You have your historical data that you might keep in Hadoop. You have your index data that you might keep in a database. And you can do analytics on top of all of this data. So you have things like real-time applications that are interested in the data that arrives now. You have historical analytics that run through the last 10 years worth of data, and you have sort of request-response applications that need to go against the database. And then you have what I like to call continuous applications. So these are applications that are running 24/7. They are interested in the real-time data. They might also be interested in the historical data. They might actually go back in time and reprocess, or they might start from a past point of time and finish in another past point of time. So stream processing is really a way to unify all of this, so unify continuous application, real-time, and historical analytics, and use basically one technology for that. Streams are becoming a very natural representation of the data, so most data arrives in the enterprise in the form of streams, and it becomes very natural to actually process it that way. And what we believe in is that data streaming is really the next programming paradigm for developing data applications. And if you're not thinking already in terms of streams, in terms of stream processing, then you probably will in a bit. So I mentioned that a lot of people are already doing stream processing without even realizing it. This is an example of how you do stream processing, aka this continuous application, so with Hadoop. So basically what people are doing, imagine the time flowing here from the top to the bottom. There is a continuous ingestion pipeline that gets the data into the system, and then you chunk this data. You divide this data into chunks. You write a file for each of that chunk. You probably name the file as begin date, end date. Then you schedule some kind of Hadoop job on that file, and you get the result. And most companies started doing that, let's say, monthly or weekly, and most companies switched to daily because they're very interested in getting the results faster. Many companies switch to hourly or are trying to switch to hourly. So it just goes down and down. Another idea that was, or maybe still is popular, is the so-called Lambda architecture. And there the idea is that you do your continuous application exactly the same way, but you actually duplicate your data flow from the input data and your processing logic, and you have two pipelines that are running at the same time. One is the previous pipeline with the Hadoop jobs that we saw, and the other is a streaming job, typically implemented with Storm. That's where the Lambda architecture comes from. And basically, these two things do exactly the same thing. It's just that the streaming job does, gives you the results faster, but typically the results are not accurate. Whereas the repeating Hadoop jobs give you the result at the end of the day, but these are actually the correct results. So these two ways is two very popular ways of how people implemented streaming in the past. There are several problems with that. The first is that we are using a lot of systems to do something very simple. Imagine that this is an application like count number of users grouped by country in the last hour. Yeah, that's it. And you want to use HDFS and Hadoop jobs and schedulers and chunk it into files and then put in Storm. I mean, it's just too complex. There's no reason for that. Time here is central to the problem. So most of the data basically has a time dimension and arrives by a certain time. But here we are not dealing with that at all. Yeah. So for example, if we are doing hourly batches and we want to change to half an hour, that just becomes very, very hard. The next problem is what is called out-of-order event handling. So typically in the real world, especially if you're talking about machine data, distributed systems, or mobile applications, data does not arrive at the order that you would like it to. So the order that you process the data is not the order that the events actually happen in the real world. And there's very little that you can do with that architecture. And finally, since we're batching data here and creating these files, it's very unclear, what are the boundaries between these batches. It's sort of clear if we're doing hourly batches, but if we want to sessionize, create sessions for our users, it's very hard to create this. So all of these problems magically go away if you actually follow a different architecture, a streaming architecture, where the application is basically push-based. So here you don't have the notion of batch processing, don't have the notion of chunks, at least at the user level. What you have is a continuous flow of data that is stored in a combination of a message queue like Kafka and permanent storage like HDFS, and you have a stream processor that does the analytics on this data and then either stores it or gives it to another team for some kind of application, or gives it some database for serving, et cetera, et cetera. And typical implementations of this is Kafka for the message queue, a variety of things for serving and storing Cassandra, databases, NoSQL and SQL databases, Hadoop for archival, etc., and Apache Flink for the stream processing. And basically, the rest of this talk is why use Apache Flink for stream processing, right? So there are a lot of alternatives out there, but what we believe is that right now, if you want to use something that is open source, there is absolutely nothing that can match Flink in a variety of dimensions. And these are the dimensions. The first is performance and efficiency. The second is consistency and repeatability. The third is correctness. The fourth is just all the rest of the features that you need to actually put this stuff into production. So basically, if you wish, the long tail. And the final is the community around the project. So let me go through each of these very briefly. Oh, should I use this? Okay. So performance and efficiency. So when we're talking about performance in stream processing, we usually care about two things. The first is latency, and the second is throughput. Latency basically means what is the end-to-end latency between when a data record arrives and when do I get my answer. And throughput is how big of a problem can I tackle. Yeah. So a while back, Yahoo, the Storm team at Yahoo, did a benchmark and they published it that compared what was then Flink, the versions of Flink, Storm, and Spark streaming And they focused, so what was nice about that was the first streaming benchmark that was kind of inspired by a real world application. And they were focused on measuring latency. So what they did was basically scale the throughput to a moderately low number of events, so 180,000 events per second. That was in a 10-node cluster. And then as they scale the throughput, they measured what is the 99th% latency of each of these systems, meaning that 99% of the results arrive within this latency. And the basic thing that they found was that in Spark streaming is a streaming solution that internally is based around this idea of batching things in small batches and then issuing these jobs. And there they found a trade-off between latency and throughput, whereas in Storm and Flink, that are based on actually stream processing, they did not find that throughput. So you can get sub-second latency with Storm and Flink as the throughput goes up. So that was nice, and it really, but it was very focused on one of the dimensions, latency. And the other problem was that none of these jobs, as implemented in the Yahoo benchmark originally, were correct under failures. So if you had a failure with this job implementation, you would have data loss. So what we did is we basically took this benchmark and we extended it. And the first dimension that we extended it was correctness. So we used the facilities in Flink that actually guarantee to you that your results will be the same if you have a failure and if you don't. And we try to scale the throughput way beyond what the Yahoo team did, using very similar hardware. So basically what we managed to do was scale Storm to more than double of the original benchmark, so 500,000 events per second. And then we scaled Flink to 3 million events per second. And at that point, the bottleneck became the network bandwidth between the Kafka cluster and the Flink cluster. So what we did was basically move the data generation inside the Flink cluster without using Kafka, and then we scaled Flink to 15 million events per second. So what you get here, what is really the important thing is, first of all, you get correctness. So these Flink jobs are guaranteed to give you correct results with or without failures. And you get the ability to tackle much larger problems with low latency. So you're not limited to problems of 200,000 events per second, but you can do much more. Now, is that important, right? So there are two things. So we can get there with Kafka. Yeah, the fact that we got there without Kafka is just an artifact of our measurements. Yeah, if we had a higher bandwidth between the Kafka cluster and the Flink cluster, it was just the hardware that we had at that time. But you can get the same number with proper Kafka and Flink. I mean, it's not that Kafka is a bottleneck here. It was just the network connection between the two clusters. Kafka can easily scale to that number. The problem was that the connection between the Kafka cluster and the Flink cluster was 1 gig, basically. Yeah. We have been experimenting with other things, and we have gotten this number even way up. Yeah, because to increase the throughput, you need to increase the batch size. That's the idea between the micro batches. So that's how you get your latency to increase. Yeah. So there's basically this trade-off there. You have to select the right batch size. Yeah. So two common things is so number one, lots of people say my business is not a low latency business. Yeah, I don't need millisecond responses. I just don't have that business need. That's fine, right? But even then, you don't need unnecessary trade-offs. Yeah. So this trade-off between latency and throughput, or the trade-off that people thought before that I'm either using Storm and I'm getting weak consistency guarantees and low latency and low throughput, or I'm using Spark and I'm getting exactly one consistency and high throughput. So these trade-offs, you don't have to deal with them anymore. You can get everything at once. Yeah. So that is really the cool thing. So even if your business does not depend on low latency, this thing is helpful to you. And many times you actually need to have sort of your continuous application reporting, let's say every half an hour, every hour, but also would like to get an early result out, for example, to build a real-time dashboard. Yeah, and there low latency helps. And another thing that we're often hearing is that we just don't have so many events per second, and we never will. Yeah, you know, our business does not have so many users. It will never have millions of events per second. However, what this gives you is actually the ability to tackle your problems essentially with less hardware. So first of all, it gives you efficiency. So you don't want to be spending, you know, all your money to your AWS bill. So if you can do everything that you've been doing with 200 nodes, you can do the same problem with 10 nodes, that's good for you. And the second thing is that high throughput also enables new applications. So I will talk a bit about later about an application where we do reprocessing. We're going back to the stream and fast forwarding through the past. The second thing that is important is consistency. So the first thing was performance, the second is consistency. So there are two kinds of streaming applications, stateless and stateful. Stateless applications, think of, let's say, filtering a stream, right? They just see one event and they do something with that event. Stateful applications are the most interesting ones, and they basically keep around state, be that a key value state or some kind of window or whatever. And the question is, how do we actually ensure that the state is correct if we have a failure? Oops, sorry. So usually the definitions that people use here are the following. So the term at least once is, let's say, imagine that we were counting, right? And our state is a counter. If we have at least once guarantees, then we might overcount, but we will not undercount. At times, people have used this term to also undercount, but I think the correct use is exactly that. The term exactly once means that if you have a failure, your count, your state will be exactly the same as if you never had a failure. Yeah, simple. And what is important to note is that this applies only to state that you keep internally in the stream processor, aka Flink, not in state, for example, the results that you export to a database. Yeah, if you worry about these results also being correct, yeah, if you have a failure, then you need what people call end-to-end exactly once, which means that, you know, from the beginning, from Kafka to, let's say, Flink and then Cassandra, everything is guaranteed to be correct. So what Flink gives you right now is exactly once for state in Flink. And if you use specific sources and sinks, it gives you end-to-end exactly once. So sources and sinks need to be able to cooperate with Flink's internal checkpointing mechanism. One example is if you're doing Kafka to Flink to HDFS, that guarantees to you exactly once. And the way that Flink does this internally is basically by taking snapshots of the whole of the state. So imagine of taking a photo of how things are happening right now, but without ever having to stop the data flow. So these snapshots are basically drawn in a distributed and asynchronous way. This has been published. We call it the ABS algorithm. It's based on Sandy Lamport. I think Flink was probably the first one to do that. By now, I think other systems are also based on that. I heard both open source and closed source. And the really cool thing about this way of doing consistency is that it really gives you exactly once with low latency and high throughput. So you don't have these unnecessary trade-offs that you had in the past. The next cool thing is that we can actually take this checkpointing mechanism and make it available to the user. So this is what we call Savepoints. So Savepoints is a super cool feature. If you're using Flink, you have a streaming job that is running 24/7, right? And then you want to say, okay, I want to take a snapshot of this job right now. So, you know, using the command line interface with one command, you do Flink Savepoint, job ID, done. So you have that, you put it somewhere in HDFS, and then later what you can do is start a job that could be the same job, or you might have, you know, found a bug and updated your code or changed something. Start another job from that save point, so you don't have to start from the beginning of time, but start from that save point, and, you know, be guaranteed that your results will be correct. Yeah, so you can actually create new versions, you can do A/B testing. Now, one thing that is coming up in Flink is the ability to actually start the job from a save point with different parallelisms, so you can scale out. Yeah. Cool. And basically the last thing that I want to talk about is correctness. And when I say correctness, I really want to talk about time. So in stream processing, there are two different notions of time. One is called event time, which is basically when did something happen in the real world. This is basically the timestamps in the records. And the other is called processing time, which is basically when do we see it in the stream processor. And these two are very different, yeah? And actually the order of event time may be very different than the order of processing time. This is an example of an out-of-order stream, yeah? So dealing with this is extremely important because event time gives you correctness and repeatability. If you rerun your application a year later, if it is based on event time, you're gonna get the same results. If you run it on processing time, the time that you actually run the application affects your results. So there are use cases for all of those, yeah? So for me, a stream processor should be able to do basically instant event at a time application. So you get an event and you have a response as soon as possible. You should be able to do sort of grouping by processing time. So as we see the events in the stream processor, it might be a little bit inaccurate, but it's faster. And you should be able to do event time, meaning that you actually wait until you know that you have received all the events for this time period, and then you emit the result. So all this stuff became very popular through Google Dataflow, Apache Beam, etc. Flink is using exactly the same philosophy with full support for event time. And the other really cool thing that you can do is really unify real-time analytics with historical analytics, okay? We call this reprocessing. I have also heard the term backstreaming. The best way I think about it is that, I sat during the last weekend and I watched all the Game of Thrones episodes of the last season. And from this week on, I'm basically catching up with a regular release schedule. So people are actually doing that with Flink in the sense that, you're going back to the past, yeah? You're starting your stream from the past. You're fast forwarding, yeah, through the past. The only way you can do that is if you have actually a stream processor with high throughput, and then you're catching up to the present. You can actually have different versions of jobs, go back, a year, 2 years, whatever. If you can actually process a year worth of data in a few hours, you can actually do that. So you can basically do historical and real-time analytics with the same system. Not fully auto yet, but so we are working on dynamic scaling, which does exactly that. The first feature will be, I think is in the master now, and the first feature is essentially restart from Savepoint. So the only thing you would have to do is at some point, as a user, do one command. You can also schedule it with a cron job or whatever. So this is going to be available soon. So final point, we talked about a lot of these things. So event time, operational and performance features, stateful streaming, the ability to define windows, exactly one semantics, save points, lots, a super rich API that is also very, if you want to do something basic, it's super easy to use. If you want to go and do very powerful things, you can actually do them. As a present, you get a full-fledged batch processor in the whole package. So I actually talk about the runtime of Flink, which is a stream processor and the data stream API of Flink. On top of the same runtime, there's a dataset API that gives you full-fledged batch processing with actually very good performance. So you can basically use the system for a lot more. Some of the upcoming features, some of them even available in Snapshot right now, that I hinted is exactly dynamic scaling and resource elasticity. The first version of SQL is in the master. It has most of the constructs for batch processing and simple stateless stream processing. We're working on adding windows to SQL for that. There's a CP library to do this kind of complex event processing. Some work there. Lots of work on supporting things like Mesos, Kinesis, Cassandra, other databases, security, a lot more. So by now the Flink community is actually a pretty big community, which allows it to work on a lot of these issues concurrently. Which brings me to community. So if you're interested about Flink, you should really go through the resources in the blog at flink.apache.org and at dataartisans.com. The Flink community is growing like crazy right now. There are more than 180 contributors in the system. We measured it in 2015 and the community doubled. There are by now 34 meetups in most continents in the world. If you don't see a meetup where you're based, we should start one. Yeah. So this is going very, very well. Lots of production installations. King is a very big mobile gaming company headquartered in Stockholm. They make Candy Crush Saga, among others. They've been using Flink in production for a while, and they have actually built a very cool system internally where they give access to their data scientists that don't really want to open an IDE and write code. They write simple Groovy scripts, and then these are deployed as streaming programs. Bouygues Telecom, one of the largest telecoms in France, has been using Flink for over a year, 24/7, for stream processing on machine data. Zalando is one of Europe's largest e-commerce shops, so they recently picked Flink for their stream processing, and they're starting with simple jobs and basically expanding. They're changing their whole infrastructure, their back-end data infrastructure from an older approach with an Oracle data warehouse to be stream-oriented. I saw very recently Alibaba has a talk at Hadoop Summit San Jose, where they present how they have been using a forked-off version of Flink that is called Blink for their stream processing needs for a while now, actually, at an extremely large scale. And they are now working with the community to bring to go back to the open source. So basically merge what they need back to the open source and continue using the open source version. I saw recently that Netflix announced a project, they call it Stream Processing as a Service internally, so giving access to stream processing internally in the company, and they're using Apache Flink and Apache Beam for that, early stages. But still, if you're interested in more user stories, there's an annual Flink Forward conference. The last one was last October in Berlin. You can see a lot more presentations from users there. And it's happening again. So if you ever needed a reason to visit Berlin, this is it. September 12 and 13, Flink Forward 2016. And that's it. And if you find that stuff cool, of course, my company is hiring. Thank you.